In this video, we are going to see how GPS clocks work. These are a new type of clock that has been developed in the last couple of decades. A clock is a device used to measure time. In the old days, these devices operated independently and were designed to run at a constant rate. Regardless of the technology used, be it a winding clock, a quartz clock, or even an atomic clock, they were all doing the same thing, ticking away based on an internal mechanism designed to maintain a constant rate. When you hear that in relativity clocks do not tick at the same rate for all observers, they refer to this type of clock. While they are made to tick at a constant rate, they don't. Their tick rate depends on their velocity in space, the closeness to a gravitational field, and the tick rate varies for different frames of reference. Here on Earth, the differences are insignificant for our everyday use, but for critical applications, this can cause serious problems. Enter the advent of GPS clocks. While we think of GPS as the satellites that tells us our current location, GPS satellites also provide accurate time. A GPS receiver provides position and time data, and it also outputs an electric pulse every second. This is called 1 pps. For example, this is the output of a typical GPS receiver. The message is valid on the next rising edge of the 1 pps. The important thing to understand about GPS clocks is that all GPS clocks run at the same rate, regardless of their velocity, altitude, closeness to a gravitational field, or any other relativistic condition that causes ordinary clocks to tick at different rates. While different observers may experience time different, GPS clocks do not mark time for different observers. They simply tick in synchrony with each other. GPS clocks are synchronized to universal time. If you, for example, have two GPS synchronized clocks together and then separate them by moving one far away, and then bring them back together, they will still be synchronized. While GPS clocks also calculate your velocity relative to the ground, their tick rate is not affected by the velocity. This has very important uses. Most clocks in use today are synchronized to GPS time. Computer networks, for example, use GPS receivers to synchronize all the clocks of computers connected to the network. Even standalone personal computers connected to internet are synchronized to GPS time. This makes it impossible, for example, that your friend receives an email from you before you send it. Not that this is possible, but the timestamps could be mixed up unless the computer's clocks are synchronized. Banks use GPS time to timestamp transactions. Stock market trades are also timestamped with GPS time. Your cell phone is also synchronized to GPS time, either through the onboard GPS receiver or, because cell towers are also synchronized to GPS time. You no longer have an excuse to be late to a meeting because your clock is running slow. More critical applications of GPS time are in surveying and earthquake detection. Multiple sensors are placed in different locations. When there is a seismic event, sensors closer to the event will detect the event earlier than sensors located further away. GPS time is used to determine the time delay of the sensing of the event for each sensor. This helps locate the source of the event. If the sensors are not synchronized with a common clock, the sensors would still detect the event, but they cannot determine which sensor got the signal first. LIGO uses synchronized clocks to determine the direction of the source of gravitational waves. Gravity waves travel at the speed of light. The time difference in the detection of the signal can point to the direction of the source. If the signals arrive at the same time, the source has to be perpendicular to the line connecting the interferometers. If the signals do not arrive at the same time, the angle of the source to the line connecting the interferometers can be estimated. The amplitude of the signal received is further used to pinpoint the most likely direction of the source. GPS clocks realize Newton's time description that there is a common now for all observers, regardless of their frame of reference, that events can be timestamped with a clock common for all observers. While GPS operation is limited to near Earth, in theory the system can be expanded to the whole solar system. GPS receivers can also output a 40 megacycles signal synchronous with the 1 pps that can be used to increase the resolution of a timestamp as far as technology will allow. We can also use GPS clocks to refute some claims from relativity with regards to the non-simultaneity of events. The most common example of non-simultaneity is the case of simultaneous lightning strikes. A train moving past an observer is hit by two lightning bolts, one at the front and one at the rear. The observer on the ground sees both strikes at the same time. Another observer on the train sees the lightning bolt at the front first, and then sees the bolt at the rear. This occurs because the train observer is moving towards the front. The observers do not agree that the events are simultaneous. This is 20th century logic. It harks back to the days when technology was limited, and observers relied on their own senses. Relativity is the only branch in science that wrongly rely on what an observer sees to time-stamp events, and it never updated their explanations to account for modern instrumentation. Events do not occur when an observer sees them. Events always occur before we see them. We can address this discrepancy by installing GPS clocks at the front and rear of the train. When the lightning bolts strike, they get time-stamped by the clocks. The clocks run synchronous with each other for both observers. The observers must now agree on whether the bolts strike simultaneously or not. There is no other option. Consider also the case of a large log going into a short barn. Length contractions are used to close the doors simultaneously, but from the perspective of the log, the doors do not close at the same time, but one first and then the other. With GPS clocks, we can now determine who is right. GPS clocks located at each door can timestamp when each door closes. The clocks will tell if the doors close at the same time or not. There is no paradox. We hope you have enjoyed learning about GPS clocks and how they work. The uses of the GPS constellation just keeps expanding by the day.